the book. We're going to talk about the dynamics of covering maps of the annulus.
Thank you. Thank you very much. Thank you for coming so early. Well, you have an hour to sleep now. The theme of this talk is the dynamics of covering maps of the annulus. We're working with some friends in Montevideo with Jorge Iglesias, Aldo Portela, and Juliana Xavier. And well, a covering map of the annulus is a map having a degree. The degree is given by its action on the fundamental group. You have that the fundamental group of the annulus is the set of integers. And so the induced map is a multiplication by d. So the geometric meaning of this is that you have a curve winding once around the annulus. The image of this curve will give d, will wind d times around the annulus. We will, throughout this talk, that d is different from 1 or minus 1, because in this case it is a homeomorphism. The case of homeomorphisms is very different. No techniques are in the intersection of at least for the moment. We couldn't find intersections. So there is one thing that is the big difference that you have in the direction of the annulus, in the direction of the curve, the non-trivial curve. You have an expansion because a curve that gives one, winds once around the circle, the middle circle, will wind d times, and so you have there something that is like an expansion, okay? Well, literature about the subject is very small. There is a family of maps given by this formula. A kind of skew product that was used and was where lambda is less than 1. This map has been studied a lot of time ago by Sititsky, was the first who introduced this map to exemplify an attractor that is hyperbolic but not stable when tau is equal to 0. Okay? Then there was works studying invariant measures by Tsuji and also by Avila and Wetzel. And there is an article by Bamon, Kiwi, Rivera, Letelier, and Ursua, Ortu, working with the topological properties of the attractor that lives here when tau is different from 0. I think that this family is very interesting, but we still don't know its generality, okay? But a systematic study of the dynamics of coverings, I never have seen anything. I will talk about this. Well, our first motivation was a theorem we did trying to understand stability 2 or 3 years ago, saying that if you have an attractor on a surface, an attracting set means only that there exists a neighborhood satisfying this property, and the intersection we say that the attractor is normal whenever the restriction is a covering. The one covering, okay? In this case, we say the attractor is normal. For this example, when tau is equal to 0, y equal to 0 is an attractor. A normal attractor because the restriction to it is just z at the power of d. But when you move a little bit tau, the attractor ceases to be normal. Okay? You have a preimage of the attractor intersecting the attractor. The closure of the preimage intersects the attractor. So this is not in our hypothesis. I think I will work a lot. Well, it's normal if this is a covering, and the result is that then if F is a local homeomorphism, then if F is a local homeomorphism, the immediate basin, assume lambda is connected, okay? Because it has, this hypothesis implies that it has finitely many components. So if lambda is connected, then not connected, the immediate basin of lambda is an annulus. And and F restricted to A is a D1 covering. This means that no other preimages of the attractor appear within the immediate basin. Okay? This is a two-dimensional result. For the dimension 3, this not holds anymore, okay? Or more than 3. So we also prove that if lambda is hyperbolic, then F restricted to lambda is conjugate to phi for tau equal to 0 restricted to y equal to 0. So it is z at the power of d in the circle, okay? There is only one possibility for an attractor that is normal and hyperbolic, okay? So first question is what happens when it is not hyperbolic, the attractor, if there is any semi-conjugacy between the restriction of F to lambda and the action of the ZD in the circle. First question. Second question is the following. This is true in the attractor. Maybe, and the basin, the immediate basin is an annulus. Is it true that the F restricted to the immediate basin is conjugate to phi, defined in its domain, that is an annulus, the domain of phi, I'm sorry. The domain of phi is y in R, z in S1. I'm sorry, okay, this is an annulus. So you can ask this question. The restriction to the attractors are conjugate. It is true that the restrictions to the basins, the immediate basins, are conjugate. The answer is trivially no. But I will show an example, okay? It's easy to see that the answer is no. For one who works with homeomorphisms, this is very strange, but for covering maps, this is easy to see. So okay, you have an attractor, you have a basin, a map that has every point is wandering, okay, in the immediate basin without the attractor. If you take A minus the attractor, and you take a component of this, no? Take a component, a connected component of the annulus minus the attractor. This is an invariant set that the map F is a covering in this set. Every point is wandering, but the dynamics you can have there have a lot of complications, possible complications. Okay, I will divide the talk in two parts. One part explaining a little bit things that happen for a single map, and then I will face the classification, the impossible classification, but some ideas. Okay, it's just some ideas I will give. Let me begin with this definition. I say that a map F, we are in the annulus. Let me explain a little. A map F of the annulus is dissipative, strongly dissipative, I say, strongly dissipative, if for every pair K1 and K2 compact sets in A, the annulus will be the open annulus. There exists a first number such that the intersection of these sets is empty for every n greater than an n0. Okay, strongly dissipative. Dissipative is the definition when one of these sets is 1 point. The definitions are at first sight different. I don't know. I still don't know. Well, this is another question. But let's begin with this. Strongly dissipative is when this happens. So this is a very powerful hypothesis on the dynamics. Let me explain a little bit the geometry of the maps. Think of a curve here. If I take a curve here, then the preimage of this curve, well, the d equal to 2. The preimage of this point is 2 points. So the preimage of this curve, lift beginning in this point, will be a curve like that, and the preimage of that curve beginning at this one is something like that, okay? So the preimage of a curve, of a simple closed curve, is also a simple closed curve. But the image of a simple closed curve, as I told you before, is something like that, okay? So taking preimages is a little bit less complicated, okay? I will give another definition here. Another definition is the fourth. I know here the hypothesis is, from now on, the hypothesis is F is a covering of A. A is an annulus, and F is a map, a covering of A, of the grid D, different from 1 and minus 1, okay? There is no attractor in this setting. I am thinking in a component of A minus the attractor, something that is for one who works with homeomorphisms. This is nothing. Okay, you take off from the basing, the attractor. You have no dynamics there. No dynamics, seemingly no dynamics, but it's complicated. I will show some things. Very well. So, in this case, everything is going to one side, from one side to the other, okay? It's going from one side to the other of the annulus. Very well. Let me give you another definition. I will show how to prove this theorem. F is strongly dissipative if and only if for every z in A, there exists a curve gamma closed and non-trivial such that, Z belongs to gamma, such that the preimage of gamma, intersection with gamma, is empty. Okay? So you have the hypothesis there. This hypothesis says that if you have a curve, then the preimage of this curve is disjoint from the curve.
You want the curve to be essential?
To be?
Essential.
Yes. Non-trivial. Okay. I will show a little part of the proof of the theorem because I'm interested in the homotopically non-trivial. Something like that. The preimage of this curve is a curve, again, a simple curve. The preimage of a simple curve is a simple curve.
Can you explain again why the preimage is
Yeah. Yeah. You want, well, let us do with d equal to 3 now, okay? Perhaps it is more. Assume that this point has three preimages, okay? Now I will lift this curve, okay? With base this point. If you lift this curve with base this point, then you will have an open curve, an open arc, that finishes in another one of the preimages of the point P. For example, if you wish, this one, okay? Now, I lift the curve with base this point, and the curve will be, and again, I lift like this, and then I lift the curve again with base this point, and you have a closed curve. No intersections, non-trivial. It must be non-trivial because the image of this curve is the other one. If this curve is trivial, the image is 0, and there your curve is not 0. The image of this curve is 3 to 1. Okay, you have for each point in this one, you have 3 preimages here, but are all in a same curve. You understand? It's okay. Well. So,
this compact set, you are thinking that these are outside of the attractor.
outside of the?
Attractor in the compact.
There is no attractor in this setting. No attractor. Let me draw some consequences of this definition. If you have an orbit, a whole orbit from minus infinity to plus infinity, then this orbit must get out from any compact set. So it must converge to the boundaries, okay? But it cannot converge to both boundaries, because if you make this curve, then the images of this curve will be and never, and will never cease if this curve is K1, if this curve is K1, and you have K2, a simple closed curve that is a compact set in the middle of the annulus, then when you begin to iterate this, you will always have intersections with K2, and the definition will not be satisfied, okay? So the point converges to one of the boundaries. And moreover, if you have 2 points, 2 points, x and y, and x converges to this boundary, then y, in the future, then y has to converge to the same boundary, because if this was not the case, then you make a curve from x to y, and the images of this curve are like this, and will always intersect something like a K2 of this kind, okay? So the conclusions of this hypothesis are every point goes, every whole orbit goes from one of the boundaries to the other boundary, okay? And uniformly, but I cannot explain this before proving this theorem. Okay, let me show why this hypothesis implies that S is strongly dissipative. Okay, so assume we know that this the annulus has a compactification with 2 points that are the boundaries. I can compactify the annulus with 2 points, then we get the sphere. Okay, the map F has an extension because it is a covering. I'm not using the hypothesis. If it is a covering, it has an extension to the boundaries. Okay, so in such a way that F that's clear. So you have a map of the sphere, and the points of the boundary, north and south, are interchanged or fixed. They are the only preimages of these points. The other points have D preimages, but these points have only one preimage. An example is Z at the power of D in the sphere. Okay? Very well. I'm saying that I will prove this part, so I assume this hypothesis. Then, if this set is a 2-periodic orbit, then F will have a fixed point in the sphere. I had an awful argument until yesterday, but Rafael Potri helped me and showed me that the argument is very easy. If F is a map of the sphere that has no fixed points, then it is homotopic to minus the identity on the sphere. Okay, it's trivial, and this shows that a map that is, if F does not fixes N and S, then it will have a fixed point within the sphere or within the annulus, in the interior of the annulus, and this, under this hypothesis, this is impossible, because if you have a fixed point in the annulus, through this fixed point, you will never draw a curve whose preimage is disjoint, okay? This hypothesis implies that you have no fixed points in the annulus, okay? So the fixed points should be N and S. Well, but this together, this is very simple. Together with this hypothesis, look what happens now.
F is always a local
What?
F is always a local
Local homeomorphism. It's a covering, yeah. Mm-hmm. Yeah, of course. No critical points, please. So, if you take, I will use the following notation. When you have a curve gamma that is simple and closed and non-trivial, like this, that I was speaking about, you denote by north of gamma. This is north and this is south. The north of gamma is the component of A minus gamma containing north. In case if gamma is like that, north of gamma is like that. Of course, south of gamma is the other. Assume that the hypothesis holds and take a point Z in the annulus, then the preimage of this curve is another simple closed curve. Okay? And assume that is like in the picture, that f at the -1 of gamma is contained in the south of gamma. Yeah? So, the map restricted to the north of f -1 of gamma is a D-to-1 covering from the north of f -1 of gamma to the north of gamma. You see that or not? This is f -1 of gamma, this curve. And this curve is gamma. The preimage of gamma is D-to-1, f -1 of gamma. So, as north is fixed, the preimage of this region above north is equal to the north of f -1 of gamma. So, if you see where it is located, the preimage of f -1 of gamma, this is a curve f -2 of gamma, must be here. Okay? The preimage of this curve must be here because the image of all of this is this one. Okay? So the preimage of this curve is this one. F -2 of gamma is thus contained in the south of f -1 of gamma. Okay, this is one argument very easy that I would like to explain. So the proof now goes as follows. You take K, the intersection of the south. Of course, we can follow this argument by induction, and all the preimages of gamma are shrinking to the south. So if I make the intersection of the souths of gamma, this is a compact set that contains south, and the claim that I will now explain now is that K is equal to south. I must use again the hypothesis, and must use that the map has no, well, see that Z is non-wandering. The first, every point is non-wandering because of this hypothesis, because if you have Z here, you take a little small neighborhood of Z, then the preimage of this neighborhood are two neighborhoods in f -1 of gamma, and the next preimages will be inside this set. So Z is non-wandering. It's wandering, excuse me. Well. Okay. Once you know that K is south, you have the following property. You have south here. Take two compact sets. Now I will prove that the map is strongly dissipative. Okay? We used this hypothesis, and I will prove that the map is strongly dissipative. Take two compact sets anywhere, K1 and K2. Take a neighborhood V, disjoint from one of them, of the south. Then use the idea I told before to prove that the preimages of K for some n, the preimage of K2 must be contained in V. Okay? All the preimages. Well, maybe connected or not. If it's this the picture, it is not connected, but if, okay, all the preimages of K2 are contained in V. So no preimage of K1 can intersect V. V is a small neighborhood of the south. Okay? Look at what's happening. Everything is converging to south in a uniformly. You see, this argument shows that the convergence to south is uniform. So the compact set enters, all the preimages of the compact set enter this neighborhood from some n. So, of course, the map is dissipative because the images of K1 cannot intersect K2, because V is disjoint from K1. Okay, this proves this part of the theorem, and this have some applications. Yes.
So you go back and you say that you go to an attractor, right?
Yeah. Why? Ah, yes. No, but if K1 intersects, if K1 intersects K2, if and only if K1 intersects some preimage of K2, F minus n of K2. So I put F minus n of K2 away from K1. Huh? These are not, no, these sets are compact sets. No attractor. And yeah, yes. If you want to push it forward, it is different pushing forward, because the problem of you go backward and the preimage of a curve is another curve inside, but you go forward and the argument does not works. Yes, I will talk about this in a while. Okay. So. Let me show you some arguments. Assume you don't have now any hypothesis. I want to understand the dynamics of a single map of the annulus. Okay? So I take, I assume now that north and south are fixed, and pick a point Z with the hypothesis here. Satisfies this hypothesis, then you will have a curve like this, and the preimage is on one side of the curve, or there or the other, no difference. But the argument above shows that you will have the curves are shrinking on one of the poles. So now I don't have any hypothesis, so maybe you will have here a compact set that is the intersection of the souths of these curves. Okay? So you will have the following property. This is K. K is the intersection of the souths of F minus 1 minus n of gamma for n positive. Okay, this is K. Contains south, is compact invariant, and is backward invariant also. It is completely invariant. It satisfies that the preimage of K is equal to K. So and also the preimage of the boundary of K is equal to the boundary of K. Okay? So I will show later that we can prove that the boundary of K, the restriction of F to the boundary of K is conjugate to Z at the power of D in S1. Okay? So we have the following conjecture. We cannot prove it, but some cases is that the node wandering set is always accumulated by periodic points. This is false. Let me explain a little bit more. in this generality. Assume you have an annulus, and here you have an invariant region. You can have an invariant region here, and the restriction of f to this invariant region, as the region does not winds around, is trivial, is a homeomorphism. You can do the homeomorphism you want here inside. You can put any homeomorphism and take then an extension to a covering of the annulus. Okay? So there you can put maps that have non-wandering points out far from the set of periodic points. Okay? These are not the non-wandering points I'm talking about. I'm talking about essential non-wandering points who come from regions which are not, in which the map is not a homeomorphism. Okay, let me define this. Z is an essential non-wandering point if Z is a non-wandering point, and let me say it like that. Z is not contained in a region invariant in a region R invariant where F is a homeomorphism. Well, invariant or periodic, no? Periodic. Okay? Except in these cases where you can produce anything you want, any homeomorphism you want, then the non-wandering points come from this wind around the circle, the inner circle. And I think that this kind of arguments, at least in some cases, this is a problem, a question I make. If the set of non-wandering points is always accumulated, essential non-wandering points is always accumulated by periodic points. Okay, I'd have to explain a little bit the classification problem. There is another question I don't know how to answer. If you change strongly dissipative by dissipative, just dissipative, that means that for every point and compact set, this condition holds. I don't know if these two statements are equivalent. Because the annulus is open, it's not compact. Okay? For example, for homeomorphisms are not the same. Because you can have a low flower, a petal of the low flower, you have points that come to one side to the other. And the strong dissipative means that you cannot have a low flower, a low petal. Well, let me... yes? No. No, for example, one-dimensional dynamics are always good to understand these kind of things. If you have a one-dimensional map, a covering map of the circle, then the graph of the lift is like this. Okay, but the periodic points are dense in the non-wandering set. Is it true in one dimension, this result I'm saying, or not? I'm wrong? Yes. No, essential is not. No, it's not the same thing. The lift of F? No. No, the lift of F may have.
So if the point is essentially non-wandering, when you lift it to the strip,
Yeah.
its orbit must be going to fit.
But maybe the word essentially was not happy. Essential, you think it's another thing. Essential, I say, that there is no region where the map is like this one. No, because imagine that you have a two periodic point. Imagine, okay, let me show you. I know what you are thinking about now. Instead of making a sector here, I will make a two periodic sector. Okay. This comes to this one, and you have here periodic points, but you don't see these periodic points in the lift.
But he's saying that when you return to the same neighbor, the universal grammar, you go to another preimage. And you don't return to the same preimage, but you change the preimage in the universal. I think that
Maybe. Yes. Yeah. No. Because I'm sorry, but the example is a two periodic point. You have to win the round after. Okay? I don't know. Well, semiconjugacies. Let me show first why the first assertion I made, why the basins are not conjugate, even when the attractors are conjugate. So let me say that you have, I will construct an example, F, that has a covering, the annulus is covered by fundamental domains. Okay? So F carries an to an plus 1. And if you take a point in the boundary of an, this comes to the point. You act as ZD in each boundary. Okay? You have A0 here, A1, A2. Okay? So this circle goes to this circle, and it is Z at the power of D. Okay? But I take a point F, I take a point P in A0. I will produce an example such that the following holds. There exists a point P in A0 such that if you take the n power of P and then this belongs to an, okay? And if I take it back to A0, I will have D at the power of n points, okay? I will produce an example such that if I take the union of these things and take the closure, this gives all the fundamental domain, okay? So think again at the example of the beginning of the function phi when the function tau is equal to 0, okay? In this example, you have an invariant circle that is an attractor, and every circle, every perfect circle, is mapped on another perfect circle 2 to 1. Okay, it has an invariant foliation, forward invariant foliation by circles. Okay, if you have a conjugacy or even a semi-conjugacy, from this, imagine that you have a semi-conjugacy from this to this. Then this annulus, A0, okay, the annulus is like that. The point P has an image. So this set, the image of this set is contained in only one curve. Because when you make the same thing, pick a point here, H of P. This is H, okay. Pick a point H of P. Make n images of it. You will have a point here. Now take the preimages, n preimages, and you will have a lot of points in this circle. But H has to send the points of this set to these points, so H must send an open domain to a single curve, so H will not be surjective, for example. So there is no semi-conjugacy. Okay? What can we do? We must understand semi-conjugacies with the map in the S1. Okay? That's the way we can classify or have a hope to classify the dynamics. So I will say now that F is SC if it is semi-conjugate to in this one. So we are looking for conjugacies like this, or semi-conjugacies. A semi-conjugacy is a map of, as we have here the same fundamental groups, a semi-conjugacy will be a map that is the identity in fundamental groups that carries 1 to 1, the curve 1 to the curve 1. This is a semi-conjugacy, of course, makes the equation H has to well, there are two cases in which we can find shadowing. This is more or less the same idea as always. I will put the annulus, the lift of the annulus like this, and I put R like this, and if you, score, sorry, and the image, we have a homeomorphism. F tilde is a homeomorphism. If the hypothesis, I put in a hypothesis, if the image of this curve is bounded, yes, if the image of this curve is bounded, then there exists, this hypothesis implies that there exists a unique, for every, the shadowing property is that the following, for every xy in the covering, in the lift, if you denote this by xn, yn, then there exists a unique y in R such that yn minus d at the power of n y bar is bounded. Okay? This is the shadowing argument. The hypothesis we need is that there exists one curve in the lift whose image is bounded. Huh? The image. No entendi.
The image of the curve is bounded.
Yes.
But it sounds like
No, the annulus is open. Okay? Maybe it may happen that
your analysis on the other position that I always.
Yes, I'm sorry. I know that.
Okay.
I'm sorry. Yeah. Juliana is always saying this to me. But
Your analysis is laying down.
yeah, I'm sorry. Yeah, you're always thinking in sleeping. Okay, this is bounded, and so the semi-conjugacy is y bar. So the image H of xy will be y bar, and you have a semi-conjugacy. Okay, just this mild hypothesis. This is the argument called shadowing. The other argument is called connectors. A connector is a connected set that joins the boundaries, and is not trivial. And is trivial. Okay? A connector is something like that. Connects the boundaries of the annulus, and is trivial. okay, and disconnected. So, if you have an invariant connector, then you have a semiconjugacy. Why? Because you take the preimage of this connector, you send this connector to 1 with H. The preimage of this connector is another connector, if D is equal to 2 always. So the preimage, you send this to -1, and then you take the preimages of this. This is sent to I, and this to -I, and you continue and gives continuity. Okay, trust me. So if you have an invariant connector, you have a semiconjugacy. If you have a free connector, the image of a connector, I will make the connectors simple. The image of a connector is disjoint. A free connector, the image of C, is disjoint from C. Then also you have a semiconjugacy because the preimages of C are disjoint from C. You have two preimages. As C and f of C do not intersect, then the preimages of C cannot intersect C, and they are disjoint, of course. So you have here that this set is sent to this one. Everything but C. Okay? So you have here an invariant region. You go backward and you find an invariant connector. Okay? So it remains to say, just to say that not every map, not every covering of the annulus is semi-conjugated to ZD. I'm sorry, but the example is a little bit difficult to explain. Let me just say an idea, very, very small. It seems we spent a lot of time trying to prove this, finding these conditions, and trying to prove that you have a free curve, a free connector joining the boundaries. But well, I have no time really to explain the example. So let me tell you if you have a question to make you. The example is infinity, yeah. See, and the example, if you take the inverse limit, is semi-conjugate to the solenoid. The example, moreover, has a covering of fundamental domains. It is strongly dissipative. Every point goes to the boundary. But in the boundary, it becomes very crazy. Okay? So we start to study. To study a map that has a covering of fundamental domains, I say covering of fundamental domains because it is not the same as say to has one fundamental domain. One fundamental domain, the image is not a fundamental domain, as Sanata says. So the hypothesis of having a covering of fundamental domains is stronger. If you have a covering of fundamental domains, you have a sequence of coverings of the closed annulus. Of course, in the closed annulus, there is semi-conjugacy in the closed annulus because the first hypothesis I draw is true. So now to study this set, for example, I think that the function f is semi-conjugate if this family is normal, for example. We have some cases proved. Okay, and the example, I told you that the counterexample is in inverse limits conjugate, semi-conjugate to the solenoid. That is strange because always you think that the semi-conjugacy would. Okay, okay. I thank you very much. I'm sorry for.